we are into the second one now. So in our next slide, we'll look at that in detail, right? Okay, so 7.21 figure shows questions on series parallel network. We have calculated total resistance in figure 1. That is this, all right? We have calculated the total resistance here. So the next one we're going to calculate is the total resistance in figure 2. That is this, all right? We will do so in figure 3 and in figure 4 respectively, as I earlier mentioned. So without wasting time, let me once again urge you, my friends, my returning subscribers, my new subscribers, remember to subscribe, remain and promote this learning platform. All right, give me some thumbs up, share with your friends, share with your networks, share with your students. Remember to put on the post button notification so that each time contents like these are uploaded, you'll be among the first individuals that will be notified. Don't forget to like and then give some thumbs up. That topic you want me to treat in physics, in chemistry, in mathematics, in whatever science topic you want me to teach, drop it in the comment section and I will do that for you. Thank you. So let's quickly look at what we have got to show in our next slide. In our next slide, we are going to have another simple series parallel network. Very simple indeed. Okay, we are not going to waste time here. So we illustrate our network quickly and label it accordingly, right? So let's see. The first goes this way. We have 3 resistors in parallel, and then at different positions we have 2 resistors in series. So that is a different thing altogether, which we must be very careful the way we calculate each and every one of them to avoid running into some amount of trouble, right? Okay, so we are going to try as much as we can put our diagram down as neat as possible and then label as suppose as we expected, right? Okay, so that is it. We have some noise in the background from the vehicular movement around, but never mind, we are going to make sure we do justice to what we are doing now. All right, so this is yes, another series parallel network of resistors. Okay, very, very interesting. Look at this. This is awesome. This is great. So if we learn how to draw these things like this, it will help us to make a very clear decision on how to calculate problems involving something like this. So the first one is 10 ohms. 10 ohms, right? Good. This one is 10 ohms. Here is going to be 3 ohms. All right, we have 3 ohms, we have 4 ohms. So we have 3 ohms, okay? We are going to fix them one by one. All right, so here we are going to have 4 ohms. We are going to attenuate our writing so that it will contain in that small space given. All right, so the second resistor in the parallel section is 4 ohms. Then the third resistor in the parallel section is 5 ohms. Good, this is 5 ohms. We better write this in a very clear way. All right, so that we don't run into some kind of misunderstanding here. All right, good. So let's see what we have got. We are just trying our best to make sure that the diagram is properly done to avoid unnecessary confusion that our learners will experience, but we don't pray for that, right? Okay, this is 5 ohms. Good. So the last, not the least, is going to be just 6 ohms. All right. Boom. Our diagram is complete. So what do we do next? Very simple. We begin to apply the necessary formula here. So because we have 2 resistors connected in series at different points, we are not going to start with them. Let's first of all clear this. Look at this section. This parallel section is the first we are going to clear, and then we now add up, right? Good. So let's begin. The parallel formula is 1 over RT. RT, okay, the total resistance for calculating resistances connected in parallel is what we are stating quickly so that we don't waste time. Then we have 1, yes, all over R1. We are going to do it to the number of resistances we have in the circuit, R1, okay? In the parallel section, yeah, parallel section, not all the resistors offering resistances in the circuit, but the parallel section is what we are doing now because we are calculating the total resistance in the parallel section, right? Good. So 1 over R1 plus 1 over R2, okay, representing resistance 2. Good. This is R2. And then we move again, have 1, okay, plus 1 all over R3, representing resistance 3. We're going to do it as neatly as expected of us. Good. So let me quickly change to this. This 2 is not looking good, okay? I want to make it look nice. Once we get the formula, every other thing is very, very simple. Good. Our 2 is better now. So what do? We quickly substitute. We can substitute here to save space, all right? It becomes 1 all over R1 here is 3, R2 is 4, R3 is 5. So we go in that order. So we have here, we have 3, okay? Good. Then plus, we continue that way, 1 all over the R2 there is 4, right? 4, very clear. Good. We move on again, plus 1 all over R3 there is 5. Without wasting time, we put down our 5, not minding how it looks. Good. It looks good. Fine. So what do we do next? We find the total resistance here by first of all identifying the resistance in the LCM of this. Okay, let's do it in a very nice way. Let's remove this. Okay, we can start from here. We start from here. Since we have identified how this can be solved, the next thing we are going to do is to find the resistance, the LCM of these resistances, especially the denominators, right? So 1 all over RT, I want to demarcate this so that you see how my solving goes. Good. So 1 over RT, I am starting from this point, RT, okay. Now we are going to look for the LCM of these 3 denominators. 3, 4, and 5. I repeat, 3, 4, and 5. They are the denominators. So we need to understand that denominators here, we need to find out the only number that they can divide individually and there won't be any remainder, right? So we have 3, 4, and 5 can divide. They can divide a certain number that will be no remainder, okay? The best way to do it is to multiply them out. 3 times 4 is 12, 12 times 5 is 60. So we can go with the 60, right? Good. 60, we just write 60. That's the best way, the best and the easiest way to do it is to just multiply out whatever they give you. Each and every one of them can divide without any remainder, right? So if 3 divide 60, it's going to get 10. 10 times this one is remaining 10. It doesn't change, right? We still have 10, right? Then we put our plus sign quickly. Now 4 divided 60 is going to be what? It's going to give us 15. Each we get 15, and then 15 times 1 remains 15, right? Good. So nothing has changed as well. We are still doing the right thing. We'll put our plus sign again for the third resistance, right? Extend our line to accommodate it. 5 divide 60. Let's see what happens. 12. All right, if 5 divides 60, each will get 12. Very, very important here. Good. So let's extend our divider. All right, good. Now it's very clear, but that is not the end. What do? We continue equal to. All right, now we come in this way. 10 plus 15 is 25. 25 plus 12 is going to give us 37. I repeat, 10 plus 15 is 25. Then 25 plus 12 is going to give 37. 37. All right, 37. Good. 37 all over 60, because 60 is the LCM and at the same time the denominator. Right. So what do? Very simple. We bring down our 1 all over RT. We bring down our 1 all over R subscript T, right? Good. Now, we have not finished. We need to find the value of RT, not the inverse, right? What do? We now multiply both sides. We multiply both sides, okay, with inverse. Something is mixing up here. We need to clear it immediately to avoid introducing error in our solving. Good. So we go back, pick our ball pen once again, all right, and then introduce inverse. Good. We introduce inverse at the left hand side. Also introduce inverse at the right hand side. So whatever happens at the left hand side must correspondingly happen at the right hand side. That is what we are doing now. So with this inverse, we take care of 1 over, and we are left with RT. We are left with R subscript T, capital T. Good. That's what we are left with. So what happens here? What happens here? This inverse, listen to me. This inverse, we just invert the whole thing. We change this. We bring up 60 and then take down 37. So we have at that point 60 comes up, right? 60 comes up, good, and then 37 comes down. That is it. That's the function of inverse in this case. Good. We have succeeded in finding the total resistance of offered by resistors in parallel section. Okay. What do we do now? We now connect the whole circuits in series with this total resistance of parallel. Let's just put P here to indicate it's for parallel section. Good. So we now redraw this. We're going to redraw this to accommodate from first to the last one. This is the first one, which is 10 ohms. Right? Good. We are trying to find the total resistance in the network now. After finding the resistance in the parallel section, it is time for us to find the total resistance in the entire network of series and parallel of resistors. So the next one, we look at this. Okay, this is a resistor 6 ohms. So we just put it there, 6, right? 6 ohms. Good. Then the one we found, look at the one we found is going to be that way. I'm going to leave it that way, right? We leave it that way. Becomes 60, right? All over 37. We put it that way. Something is getting mixed up there. We need to do it right so that our learners will not find it confusing. So let's clear off this. Let's just do something meaningful here so that we retain the interest of our learners. Very good. Now let's go back, pick our ball pen once again, redraw what we did before to make meaning, right? Good. So what do we have? We have that 60 should be up. All right, 60 should be up. Then all over 37 We're trying to fix it well so that we don't mix things up. 37. Good. Things is better. Now what do? We are going to calculate. We are going to calculate the total resistance in series, because we have succeeded in connecting all the resistors offering resistances in a single loop, right? Good. Or like a chain. So the total resistance in series, once again, let me demarcate this to show that I'm entering into a new phase of calculation, which is RT for total resistance in series, right? Is now going to be, the total resistance in the network is going to be 10 ohms, right? It's going to be 10 ohms. Now we have 10 ohms plus, we have 60 over 37, 60 over 37, all right? This is 60 over 37. Let's quickly look at that. We pick our correction fluid once again, or eraser, to make sure our diagram looks neat, and our solution should also be properly explained so that we don't have any sort of confusion here. So we have this all over 37, right? All over 37. Good. We are making progress. We are making progress, and this becomes plus the last but not the least resistor. Look at this, 6 ohms. So we are going to just add 6 all over 1. Since we now have fraction there, 1, we have to come here, put what? 1. Good. So with this, we are making progress, serious progress. What do we do to calculate the remaining aspect of it? To simplify all this, what we do, we multiply all through. Okay? We multiply all through with 37 and it vanishes. Okay? So 37 times 10 is going to give us 370. Alright? It's going to give us 370. That's what it's going to give us. Alright? I know it's going to be a long process, but learning is all about exercising patience and learning it once and for all. Right? Okay, so it's 337 multiply 10 is going to give us 370. That is 370. Alright. Good. Okay? Very good. Now we go again. 37 comes here. It's going to cancel out. We have only 60 remaining there. Right? Okay? Then 37 go again against 6. What are we going to have? Let's do it this way. 7 times 6 is 42, right? Good. We write to carry what? 2. Let's do it this way. 7 times 6 is 42. We write 2. Holding 4. Yes. Yes, we are right. Then 6 times 3 is 18. 18 plus 4 is 22. So total we are going to have 22. Right? Good. So we come down, we bring down our calculation here is going to be 2. Alright, 2 again. And then finally we have 2 once again. Good. Alright, so calculate this. If we do this the normal way, if we now finally sum up this, we should have something very important here. 370, excuse me, this is 370 plus 60. So we have, and then 222, right? So if we calculate this, very simple. I like being practical in what I'm doing. Let's see what happens. We have 370, right? 370, first of all. We add 60. Let's see. We add 60 to it. What happens? Remember, we are adding 60, right? So let's see what happens here. When we add 60, we have 0 here. And then we have 3 here, right? And finally, we bring down our what? 3. We have 4, okay? Because 6 plus 7 is 13, right? 3 carry 4. We bring down our 4 at this point. So we have 430. 430 plus this. Very simple. Let's go. If we add 430 to 222, what do we have? We have 652 ohms. We have 6, good. We have 5, right? And then finally we have 2. And our unit is going to be ohms, good. Total resistance in this figure 2 is 652 ohms. Really, this has really taken us time, but it's worth it. Learning is always a continuous process that has to be done with patience, all right? That is it. Thank you for taking time to watch this. I urge you, subscribe. Come on, subscribe. Okay, let's do it this way. Put in the comment box, drop in the comment box the topic in physics, or the topic in chemistry, or the topic in mathematics that you want me to teach. I will do that for you. Notwithstanding, you need to support me. Give me some thumbs up, share with your friends, with your networks, with your students, and then some thumbs up, some likes, okay? But turn on the bell button for constant notification, so that each time something like this is uploaded, you will be among the first set of individuals that will be notified. I am solving it real before you, all right? See you there. Thank you so much. I'll be linking other videos somewhere here or somewhere there.